Good afternoon, folks. How are you today? We are in week number 10 of our semester. And this week, our focus would be on numerical differentiation. Okay, let's see. Numerical differentiation. So, why do we want to learn numerical methods? Well, the reason is you know how to differentiate a function, but the function may be in tabular form. Then you cannot use your calculus techniques. The function may be embedded in hardware or software. So the function may be a black box. So if we want its derivative, we need to take it numerically. The function may be a complicated function. So you may not want to spend the time differentiating it. So here is our problem. So we are given function in some form. And what we want is we want nth derivative at some particular x, where n is one or more. Sorry, one or more, first derivative or more. Okay. So the formulas we use are called finite difference relations. And they come in three categories. One category called central difference, another category called forward difference, and a third category called backward difference. So here they are listed. And these formulas or relations have certain truncation error. So central difference relations have truncation error, which can be proportional to either h square or h to the power 4, h to the power 6, etc. Forward and backward difference, both, they start with order h relation, then they move on to h square, and then to h4, h6, etc. And we'll see in a moment why so. So let's see what we mean by a derivative from your calculus perspective. So we draw, and let's say this is our function, and we want to evaluate the derivative here. So this is our x. So we go to some distance delta x away. So this is x plus delta x now. This is the function at x. This is the function at x plus delta x. So we defined our delta y over delta x as delta y is just the difference in two function values. Okay. Then we say that dy dx, the derivative of y, is the limit when delta x goes to 0 of this quantity delta y over delta x. So you can see if I use this relation as shown in the figure, I will estimate the derivative to be slope of this line. Now if I start reducing delta x, let's say I reduce delta x to here, then slope of this line would be my delta y delta x. So you can see as I keep reducing delta x, eventually I will get my exact derivative value. But of course, when delta x becomes 0, I can't use this expression. So we have to use, therefore, finite differences. Delta x has to be finite, non-zero. So we have these expressions. So let's see how to get centered difference. And I'll use CD for short, order H square relation. So let's draw again. This is X, this is function X. Let's say this is our curve, and we want the derivative here at xi. So what we do is we evaluate the function at point before and after. And all our points we'll assume are spaced h apart. So that's like delta x. So this is fi plus 1. This is fi minus 1. So in center difference, what we do is we take we want first derivative, remember, we want fi prime. So we want derivative here. We want to estimate the slope. So what we do is we take the point at either side, connect them both up with a straight line, and find the slope of the straight line. And that would be our approximation. So we'll say this is approximately, slope of this line would be height of the triangle. So this triangle here divided by the width of the triangle. So that's our approximation. So this requires knowledge of 3 points. I say 3 points even though it is 2 function values, because it might have involved the center point. We need to know the knowledge of that center point anyway. Just so that you know, we will not derive it, but we will see that the second derivative formula looks like this. Let me show you. We have a table. So our second derivative formula for center difference looks like this. Fi plus 1 minus 2fi plus fi plus 1 minus 1 over h squared. So this also requires 3 points. So we say that this is a order h square formula. So these are both order h square formula where truncation error is proportional to h square. So let's see how we get it. So we'll take Taylor series. And let's expand fi plus 1 by Taylor series. So we'll get fi plus h fi prime plus h square by 2 fi double prime plus h cube over 6 fi triple prime plus, let's say, higher order terms. Fi minus 1, fi minus h fi prime plus h square by 2 fi double prime. All I'm doing is substituting minus h triple prime plus higher order terms. So now what we do is we subtract 2 from 1. So we'll get fi plus 1 minus fi minus 1. This will cancel out. This will become 2h fi prime. Cancel out. This will become 2h cube over 6 fi triple prime plus some higher order terms which we are going to ignore. So now we can find out what is fi prime. Fi plus 1 minus fi minus 1 over 2h. So this was our approximation. Then our truncation error, we divide this, take it to the other side by 2h. So we will get h square over 6, third derivative. So now you can see this truncation error is proportional to h square. So that's why these are order h square formulas. So this way we can derive formulas for any ordered derivative just by manipulating Taylor series. Okay, so we derived the first derivative formula, central difference, order h square expression. And as I said, we could derive similar expression for any level derivative. So here are, for instance, first derivative expression, order h square, order h4. Second derivative, order h square, order h4, and so on. Third derivative, fourth derivative. So let's see first the pattern. When we look at first derivative, remember these are all central difference. The order h square formula involves fi minus 1, fi, fi plus 1. I said even though the formula explicitly doesn't contain fi, we need to know either point, points on either side. So we need to know 3 points. If we go order h4, order h4 formula is for first derivative here. So notice we need to know I plus 2, I minus 2, I minus 1, I plus 1, and I plus 2, right? So we need to know 5 points. So every time we go order h square, order h4, order h6, we add points. Let's look at second derivative. Order h square requires same 3 points. So you can see same 3 points. Order h to the power 4 requires same 5 points. Okay. All right. Now let's go from derivative to derivative. Now when we go to third derivative, let's see order h square. This is order h4, remember. Order h square. So this requires I plus 2, I plus 1. Of course, there is an I in between, I minus 1, I minus 2. So this requires 5 points. So order h to the power 4 will require 7 points. So that's our pattern. Now let's see fourth derivative. Order h square. Fourth derivative requires same 5 points. And then order h4 will require 7 points. So now when we go to fifth derivative, order h square will require 7 points, you will find. Okay, we'll do a numerical example at the end. Let's look at the next category of relations. So the next category of relations is called forward difference. I'm going to use FD for short. So here we begin with a order H formula. And let's see how we construct it. X, f of x. Let's say we want to find derivative at this point. So forward difference is go a point ahead. So this is fi, this is fi plus 1. And then we connect these 2 points with a straight line, and that's our approximation for slope at I. So of course, again, we construct a triangle, height of the triangle, width of the triangle, and this is a order H expression. And you can see Taylor series tells us that. So if we write fi plus 1 is fi plus h fi prime plus h square by 2 fi double prime plus higher order terms, which we are going to neglect. So if we write fi prime from here, we will get fi plus 1 minus fi over h. So this is our approximation. You see it in the box above. And our error would be h over 2 fi double prime. So you can see truncation error proportional to h. So that's why this is a order h formula. So just like before, I have a table here. So notice first derivative, order h, requires 2 points only. Then we go to order h square, it'll require 3 points. Order h4, 5 points, and so on and so forth. Look at second derivative. Second derivative, there is an order h expression, requires 3 points versus 2 for first derivative. And you can see here the patterns differ slightly. First derivative, order h square expressions. First derivative, 2 points. Second derivative, 3 points. Third derivative, 4 points. And you can see the pattern. Okay. Now, when we go to forward difference for just the first derivative, remember order h formula was 2 points. Order h square formula was 3 points. Okay, and so on and so forth we can go. All right. Then our next relationship is backward difference relation. In backward difference relations, all we are doing is we are just flipping it. Right? So we have this curve. We want derivative here, xi. We take a point behind xi minus 1. So this is fi minus 1. We connect these two with a straight line. So we get our first derivative is fi minus 1 over h. And this is a order h relationship. So you can see backward difference relationships follow the same ideas. First derivative requires 2 points, second 3 points, third 4 points, so on and so forth. Higher orders require 1 extra point. Okay, so let's do an example. Okay, so we have given this table of values, and what we want to do is we want to find first derivative and second derivative at x is equal to 0.4 using all of these difference relationship with their errors. Okay. So I'm going to recreate the table here, x, f of x. So they are spaced 0.1 apart. You may remember this table. We used it for integration. So you know the function now. I would like you to also do it along with me. So take out a piece of paper, pencil, do it along with me. So remember, we want that x is equal to 0.4. So this is our 0.4. Right? So this is our function value, one before, one before, one after, one after, after. Okay. So our first is central difference order h square. So let's do first derivative. So our first derivative formula was fi plus 1 minus fi minus 1 over 2h. So our spacing here is 0.1, remember. So this value is 1.649 minus 1.350 divided by 2 times 0.1. And we will get 1.495. Okay. So remember our function is e to the x. So all derivatives are e to the x. And at x is equal to 0.4, we know e to the x is 1.492. So all the derivatives that we are going to find in this list, their true value is 1.492. Okay. So our error is 0.003. All right, let's see second derivative. Second derivative is fi plus 1 minus 2fi plus fi minus 1 over h square. So 1.649 minus 2 times 1.492 plus 1.350 over 0.1 square. And now we are going to get 1.500. So our second derivative is actually farther away from true value, right? Okay. Let's see forward difference order h. So first derivative is fi plus 1 minus fi divided by h. So our table, this is our fi, remember, fi plus 1, next is 649, 492 divided by 0.1. And we are going to get 1.570. So here our error from 1.492 is much larger, 0.078, because this is order h only. Let's look at second derivative. Second derivative, let's go to the formula page so you know where I'm getting these formulas from. So second derivative, order h, is fi plus 2 minus 2fi minus plus 1 plus fi over h square. Okay, so let's go back. So this is I plus 1, I plus 2. So we have 1.822. Okay, so 1.822. Let's go back. Minus 2 times 1.649 plus 1.492 over 0.1 square. Okay, let's calculate this. and I get 1.600. And now we are 0.108 away. Only our first digit is correct. Okay. All right. Now, next category was forward difference, order 8 square. This is what most people prefer, order 8 square. So let's see, first derivative. Our formula is minus fi plus 2 plus 4fi plus 1 minus 3fi divided by 2h. Okay, so let's go back. I plus 1, I plus 2. Okay, so we punch it in and we get 1.490. So here delta is only 0.002. So you might want to compare it. First derivative, order h, larger error of course. Order h square, you can see that this error is comparable, 0.003 versus 0.002. Okay, let's do one more. Let's do second derivative. So let's go look up relationship. Order h square, here is our second derivative. So minus fi plus 3 plus 4i plus 2 minus 5fi plus 1 plus 2fi divided by h square. Okay. So I plus 1, I plus 2, I plus 3. So we'll start with there. Divide by h square. And we are going to get 1.300. So the second derivative is quite far away. It's 0.192 away. All right. Okay. What I would like you to do on your own is do backward difference order h square. Get fi prime and see if you match my value, 1.485. Second derivative, see if you match my value, which is 1.300, and it has a large delta. Okay. So we are going to stop here.